we've now gained an intuitive idea of what a probability measure should look like. It's a set function defined on subsets of a sample space, the universe that we're considering. But for both technical and information theoretic reasons, we may not want to include all possible subsets of the sample space as events to consider. We do have to include a certain minimal number of events in order for the whole thing to make sense. For example, we can always take the probability of the whole sample space. That probability is 1, so we should include the sample space as one of the allowed events. If we can calculate the probability of an event E, then we can also calculate the probability of its complement, 1 minus that probability. And so our set of allowed events should be closed under complements. For similar reasons, following the discussion from the previous video, the set of allowed events should be closed under finite or even countable unions and intersections. So let's make a formal definition. The collection of events that we're interested in, the allowed events, is going to be called a field. A collection F of subsets of a set omega is called a field if that collection contains the whole sample space omega and the empty set, if it is closed under complement, if it is closed under finite union, and if it is closed under finite intersection. Now, as we discussed last time, we'll also want it to be closed under countable union and intersection. But before we go there, let's take a look at the conditions we've written down. In fact, this is not a logically minimal set. All of these are going to be true for a field, but some of these conditions can be dispensed with because they follow from the others, using naive set theory rules that we're going to have to get adept with. So I thought I'd demonstrate them now. For example, let's look at items 2 and 3. If we know both of those, it turns out we can dispense with 4. The reason is as follows. Suppose that I take a finite collection of sets, E1 through En, from our field F. If I take their intersection and consider its complement, by De Morgan's law, that's the same thing as taking the union of the complements of the individual sets. This is just to say not and is the same as or not. But here we have a collection of complements of sets that are assumed to be in F. And therefore, by property 2, these are all in F. And therefore, by property 3, this is in F. And so, the intersection of those is a set whose complement is in F. But therefore, by property 2, again, the whole set, the intersection, is in F. And so what we see is that, in fact, we can just get rid of condition 4. It follows from the other conditions. Similarly, we can get rid of the explicit requirement that the empty set be in F, because if omega is in F, so is its complement, which is the empty set. Now we have a logically minimal collection of conditions, 1, 2, and 3. But following our discussion from the last video, we're going to strengthen 3 to 3 prime, and we're going to insist not only that a finite union of events is in F, when the events are in F, we're going to insist that any countable collection of events in F have union in F. That is a stronger condition than 3. And if we have a collection of sets F, an F field, that satisfies that stronger condition, we call it a sigma field. Sigma fields are the basic groundwork for probability measures. That's the kind of collection of events that we'll always start with when we're defining probability measures and measures in general as we go forward. So before we go forward too much further, let's consider some examples. The most basic example that we should always start with is the power set. The power set is, of course, a field and a sigma field. The power set is the collection of all subsets of omega. And the collection of all subsets of omega is closed under any set operations that you want. It's closed under complement, it's closed under arbitrary unions and arbitrary intersections, be they finite, countable, or uncountable. And so the power set is always a sigma field, and therefore a field, since sigma fields are, of course, fields. So that's the biggest possible example, the largest sigma field over omega. There's also the smallest to consider, the so-called trivial sigma field, which consists of nothing other than the empty set and omega itself. You can check that this collection of events vacuously satisfies all of the conditions. Well, not vacuously for the first condition. It does indeed contain omega. How about for complement? Well, the complement of this set is this set, and the complement of this set is this set. And those are the only two ones present, and so yes, it is closed under complement. How about closure under unions or intersections? Because there are only two sets here, any union is just going to consist of unions of this one and this one, which means you're either going to get this one or this one, depending whether you include this one or not. And so this is indeed a sigma field. Let's consider a slightly more interesting example. Let's start with a sample space, omega, that has three elements, 1, 2, and 3. Here is an example of a subset of the power set. And I claim that this subset is a sigma field. What do we need to check? We need to check that it's closed under complement, that it's closed under countable union, and that it includes the sample space itself. Well, we can see that it includes the sample space. We can see that it's closed under complement because the complement of this set is this one, the complement of this set is this one, and those come in pairs. The complement of this set is that one, and the complement of this set is that one. How about countable unions? Well, it's a pretty straightforward check that if you have an underlying sample space that is finite, the notions of field and sigma field are the same, because the entire power set has only a finite number of subsets in it. If there are n elements in omega, there are 2 to the n possible subsets. And therefore, any countable union is automatically a finite union. Most of the elements that you're unioning up get repeated if you're listing them infinitely many times. And so we only need to check that this is a field, which means we just need to check that this set is closed under finite union, which means, by induction, we only need to check that it's closed under any union of 2 of them. So there's just 6 to check. I need to take this pair, this pair, this pair, this pair, this pair, and this pair, and make sure that the union of any 2 of those is back in the set. And that is a not too laborious, but kind of boring check. Let's just do a couple of them. We can, of course, ignore the empty set because its union with anything just produces that thing again. And we can also ignore any of those that include omega, because the union of omega with any set is just omega. So actually, we've reduced our consideration to just the union of these guys. And indeed, the union of these guys is omega. So this is a sigma field. How about this? Here's a more interesting example. Take any sample space omega and consider the following collection of subsets. Subsets B of omega that are countable or co-countable, have complement that is countable. Now, if we had ignored the second condition, we'd be in trouble, unless omega itself is countable. Indeed, if omega is a countable set, then the complement of any subset of it is countable. But what if omega was the real line? Then this would certainly not be a sigma field, or even a field, because the complement of a countable set in the real line is an uncountable set. Therefore, we have to explicitly include this condition in order to get closure under complements. But once we do that, it turns out that this set is closed under countable unions. Why is that? Well, let's think about finite unions for a moment. Suppose that I take two sets that are both either countable or uncountable. Or rather, suppose that I take two sets that are either countable or co-countable. If I take two countable sets, their union is of course countable. A co-countable set is one whose complement is countable. So what if I take the union of two co-countable sets? Well, by De Morgan's law, that's the same thing as the complement of the intersection of two countable sets. Since the intersection of two countable sets is countable, we have a co-countable set. Similar arguments will show you that a union of a countable and a co-countable set is again either countable or co-countable. I'll let you work out which one. And so F is a field. Now, that doesn't show that it's a sigma field, but because F is classified by two kinds of sets, two conditions, a condition and its complement, it's not hard to check that in this case, like in the case of a finite sample space, being a field is more or less tantamount to being a sigma field. If you have a countable collection of sets, each one of them is either countable or co-countable, then you can just group the ones that are countable, group the ones that are co-countable, take their unions separately, and now you've reduced to the case of considering only a union of two sets. So this F is a sigma field. So those are some examples. We will definitely see more examples in the coming lectures and in the coming slides. But before we do, we have to take note of the fact that in most cases, it's very hard to describe the entirety of a sigma field. It's often a very large, messy collection of sets that doesn't have a very nice, simple description. But we can often talk about a generating set for it that contains all the information we need to access all of the sets in the sigma field. And to meaningfully speak about that, we need the following lemma right here. This lemma says that if I take any intersection, in fact an arbitrary intersection, it could even be uncountable, of sigma fields, the result is a sigma field. Now why is that? Well, we simply have to check each of the three conditions that define being a sigma field. Let's give this putative sigma field a name. Let's call it F. We want to check each of these three conditions holds for F. For the first one, we want to see that omega is in F. What do we know? We know that each Fi is a sigma field, and therefore omega is in Fi for each I. But that is the definition of omega being in the intersection, which is F. Check. Similarly, we need to check that F is closed under complements. Well, suppose we take a set E in F. If E is in F, that means that E is in Fi for all I. But Fi is a sigma field, which is closed under complements. So that means that E complement is contained in Fi for every I, which again means that E complement is in the intersection, which is F. Check. Finally, we need to check that F is closed under countable unions. Let's start with a countable collection of elements of F. What does it mean that this countable collection is in F? It means that each of the ENs is in each and every Fi. Because Fi is a sigma field, it follows that the union of the countable collection of ENs is in Fi. And that's for each I. But that means that the countable union of the ENs is in the intersection of all the Fi's, which is F. Check. And so we see that indeed the intersection of any collection of sigma fields is itself a sigma field. With this intersection property in hand, we can now proceed to see how to better describe a sigma field by a nice collection of sets inside it. If you start with any collection of subsets, there is a unique smallest sigma field that contains it. It's called the sigma field generated by that set E, and denoted like this, sigma of E. How do we prove that such a thing exists? Easy peasy. The sigma field generated by E is nothing other than the intersection of the set of all sigma fields F over omega that contains E. Now, this is certainly a non-empty set because in this intersection, in this collection of sets we're intersecting, is, for example, 2 to the omega, the power set. The power set is a sigma field that contains E. And therefore, we're taking a non-empty intersection. It's an intersection of sigma fields by definition, therefore it is a sigma field by the previous lemma. And it is easy to see, this is a standard construction, that it is the smallest sigma field containing E, which means exactly that if G is any other sigma field containing E, then G must contain this. And that is an exercise that I'll leave to you. So let's look at an example. Here again, we're considering a 3-element sample space, omega, 1, 2, 3, which means that since the full power set is finite, sigma fields and fields are the same thing. So here, when we talk about the sigma field generated by a particular collection of sets, we're just talking about the field generated by them. Same idea. So here I've specified 3 subsets: the empty set, the full sample space, and the set 1, 2. What is sigma of E in this case? Did you think about it? By definition, the sigma field generated by E is the intersection of all sigma fields over this sample space that contain E. Now, we could start with the largest one, the power set of this omega, and whittle down from there. That's a pretty big sigma field. There are 8 elements, as compared to E, which has 3. Maybe we can find a smaller one to start our negotiations. Let's see what we minimally need to include. Right now, E is not a sigma field, or even a field. One reason is that it's not closed under complement. This set here, 1, 2, is not complemented in E. The complement of that set is this singleton here, 3. So for starters, if we're going to be a field, or sigma field, that contains E, we've got to include that singleton set 3. So let's start there. For sure, the sigma field generated by E will have to be contained in the 4-element set, empty set, 1, 2, singleton 3, and omega. Now, we might be done, but we have to check if this thing is a sigma field. And actually, it is. It's this example right here. Almost, up to relabeling. This is indeed a sigma field, and therefore it contains the sigma field generated by E, as we've written here. But actually, it's equal to the sigma field generated by E, because we can't whittle it down at all and still maintain the sigma field property. Every set in here is complemented exactly once, and if we remove any one set, we will lose that complement property. If we remove this set, we'll have to remove that one as well, and then we will no longer contain E. So we have identified the sigma field generated by this family of subsets. We had to expand it a bit, but not much. Now, to formalize the kinds of arguments that we went through there, I'm going to leave you with an exercise which you'll use a lot in identifying sigma fields. Here's the question. Suppose I give you two families of subsets, E1 and E2. I'd like you to determine if they generate the same sigma field or if they generate different sigma fields. This is hard to answer just by looking sometimes. E1 and E2 could be disjoint. They could be completely separate families of events. But they might still generate the same sigma field. How can we tell? Here's the exercise. Prove that E1 and E2 generate the same sigma field if and only if each of them is contained in the sigma field generated by the other. That will be on your homework. We'll use that exercise many times in the coming days. In fact, we'll use it now when we think about the most important sigma field that we're going to deal with, at least at the beginning of this course, the Borel sigma field. Usually when we start, the sample space we're working with is not just an abstract set. It usually has some additional structure. Many times it's going to be the real line, or an interval in the real line, or possibly a set that has nice geometry in Euclidean space. Minimally, it will have a topological structure. So let's consider topological spaces, X. Again, if you're more comfortable thinking of Euclidean space, that's pretty much the only example you'll need to know for this course. There's a special sigma field associated to any topological space, which we will use a lot, called the Borel sigma field, denoted like this, script B of that space X. And it's simply defined like this. The Borel sigma field of a topological space X is the sigma field generated by the open subsets of X. Those sets that are in the sigma field generated by the open subsets, they're called Borel sets. They can be quite a lot more complicated than open sets. For example, the complement of any set must be back in the sigma field. The complement of an open set is usually not open. It is, however, closed. So the Borel sigma field contains all open sets and all closed sets. But it contains weirder sets as well, because you have to close under countable intersection and countable union. Any union of open sets is open, but a countable intersection of open sets need not be open. It also need not be closed. For example, on the real line, we can have the following collection of open sets. These are open intervals from -1 over n up to 1. 0 is right here. What's the intersection of that countable collection? It's an intersection of open sets. However, the intersection turns out to be a half-open interval. Borel sets can be neither open nor closed, and they can be a lot weirder than this as well, as you iterate this construction, taking complements, taking countable unions and intersections. And we'll go into some of the structure of that as we go. if we're in the nice situation where the topological space is Euclidean space, then there's a nice characterization of what the open sets are. In fact, in Euclidean space, in RD, every open set is a countable union of open balls. Balls centered at some different points with some different radii. And this will be useful later on. We can even insist that the coordinates of the points and the radii are rational numbers. But we don't need to worry about that right now. So when we're taking the sigma field generated by the set of all open sets, we can consider a potentially smaller sigma field generated by just the collection of open balls. In fact, those will be the same because of this fun fact. And if you'd like to prove that, the easiest way is using the exercise. So we can think of the Borel sets in Euclidean space as the sigma field generated just by balls. In one dimension, balls are open intervals. But as we just noted, we could also consider all sorts of competing definitions, which give the same result. The Borel sets over the reals are also the sigma field generated by the set of all half-open intervals, like this. They're also the sigma field generated by the set of all half-open intervals, like this. And you can concoct a bunch of other crazy examples if you like. These Borel sets, this sigma field, will play the most important role as we go forward to developing probability theory on a rigorous measure theoretic footing.